Welcome back to Algorithms and Uncertainty. We're still talking about online learning, which means that we have this stepwise process where in each step our algorithm has to choose one of n actions, and then we incur a certain cost depending on this action. We get to know something regarding the actions, and then we keep repeating this. Our goal is to perform at least as good as the best single action. Last time we turned the multiplicative weights algorithm into an algorithm which worked with partial feedback, meaning that we only get to know the cost of the action that we chose and not the cost of the other actions. Today we will improve this algorithm, and what we will be improving on is the regret bound. But before we get started, let's first recap the notation. So as I was saying, we have these n actions. And now we have an adversary, a hypothetical adversary, who fixes cost vectors L1 through LT. And LIT, this is the cost of action I in step T. This is always between 0 and 1. And now in step T, the following happens. The algorithm chooses one action, IT, in a randomized way. It incurs a cost, L, subscript IT, superscript T. So in the vector LT, take the entry at the ith coordinate, and only then it gets to know something, and it gets to know only the cost of the action that it chose, so only the cost that it is incurring here, and not the cost of the other actions. This is what we call bandit feedback or partial feedback, as opposed to experts feedback or full feedback, where we get to know the entire cost vector. And we designed an algorithm for this setting. And we designed this algorithm actually in 2 steps. And what I've tried to do here is to summarize this entire algorithm into a single. Namely, how did we do this? Well, we had this multiplicative weights algorithm. And then we decided how to use this multiplicative weights algorithm, which actually needed full feedback. How we wanted to turn this into an algorithm which only works with this partial feedback, knowing only the cost of the action that we chose and not the cost of the other actions. And how did we do this? Well, the key thing was this LIT tilde. This was the fake cost of an action, something that we can compute based on the knowledge that we have. This is LIT divided by QIT if I is the action that we're choosing in step T, otherwise it is 0, and QIT, this is the probability that we're choosing this action. Where is this QIT coming from? This QIT is 1 minus gamma times PIT plus gamma over n. And where is the PIT coming from? Well, last time we were saying that this was coming out of this multiplicative weights algorithm. Now I've written down here explicitly what this means. In this multiplicative weights algorithm, eventually we'll choose PIT plus 1 equal to WIT plus 1 divided by capital WT plus 1. So we'll choose the probability P that we choose action I proportional to its weight. And the weight we determine how. The weight we change multiplicatively. So the weight that we have in or before step T plus 1 is the weight that we have before step T times something, and this is the multiplicative weights update. Now here I've changed the rule a bit. It's easy to see that they are equivalent, but this is more helpful for what we're doing today. We'll set the new weight to the old weight times e to the power of minus eta times 1 over rho times LIT tilde. So here, this scaling with this 1/rho, this was actually a separate step that we did last time. I've already incorporated this in here. And then we had our original rule for the multiplicative weights update was 1 minus eta to the power of lit. Now here we're using instead e to the minus eta times something. This is actually equivalent because it's just a different way of setting this eta. If you were choosing this eta to be log of 1 minus eta prime, then you would get here that this is nothing but 1 minus eta to the power of 1/rho times lit tilde. Good. So this is actually all we did so far in the past 2 lectures. In the last lecture we did this black part, this blue part we did in the lecture before. And then what we showed is the following result, namely, if we set gamma to be the third root of n times ln n over t, and eta to be the ln of 1 minus gamma, and rho to be n over gamma, then the regret will be at most this much. This is something that depends on n times t to the 2/3. This bound we've actually already seen before, or this kind of a bound, but the big question is this bound actually optimal? And it turns out, no, this bound is not optimal. We can actually improve the dependence on t from t to the power of 2/3 to square root t. And this turns out then to be optimal, which we'll show next time, by the way. But today we'll try to find an algorithm which gives us a better regret bound. And this algorithm is called the exp3 algorithm. Let's see what it looks like. Today we'll get to know the exp3 algorithm. exp3 stands for explore and exploit with exponential weights. So the idea is to combine exploration with exploration and to use exponential weights. Exponential weights, that's actually nothing but multiplicative weights. And how does this algorithm work? What does it look like? Well, we've already seen the algorithm because it is exactly our algorithm from last time. This here is the exp3 algorithm, and now I hope you see why I wrote it this way, because this is the way the exp3 algorithm is usually defined with this exponential function here. So this is why they call this exponential weights. Cool. So we'll do exactly the same things that we did here, with actually just one minor change. What did we have as parameters here? We had this gamma. What does the gamma control? The gamma says, okay, in every step I do this much exploitation and this much exploration. Because we are, with the probability of gamma, we're choosing just an action uniformly at random. So with probability gamma, we're just exploring. And with probability 1 minus gamma, we are exploiting because we're following what this multiplicative weights algorithm is telling us to do. What else did we have? We had this eta, which is this learning rate here, which tells us how aggressively do we update our weights. If eta is 0, then we wouldn't update our weights at all. If eta is, say, infinite, which is possible now, before we had eta between 0 and 1, now eta could be even infinite, then we are changing the weights drastically. And then there's one more thing floating around here, which is this row. This row, where was this coming from? We wanted to scale the lit tilde so that they are between 0 and 1. And why did this turn out to be important? Well, we analyzed before the multiplicative weights algorithm for the case where the lit tilde were allowed to be between 0 and 1. Now, here, the lit tilde, as we define them, they can be between 0 and what's the biggest number that we can get here? N over gamma. So this is why we then said, okay, let's set this row to n over gamma, because this is an upper bound on every lit tilde, and then we can reuse the analysis of the multiplicative weights algorithm. And this is what we're not doing now. We will now set this row here just to 1. So in a way, we are much more aggressively updating our weights because, well, we'll only have this eta here. We're not scaling down everything as much. But the hope is that by doing this, we adapt faster to certain situations, namely when one action turns out to be really bad. Because before, this was really going down very slowly. And what we'll still have to do, of course, is to realize, okay, now it doesn't go wrong, and nothing goes wrong in the sense that suddenly our weights change crazily. And this is exactly why we'll have to reprove or reanalyze this multiplicative weights part. But before we get there, let's once again try to write down what we're now doing. So in the algorithm from above, we just set rho equal to 1, and we will set this gamma and this eta later. And why might this turn out to be a good idea? Well, so far we only used that lit tilde is at most n over gamma. And what will we use now? We will use that the expectation of lit tilde, I hope you recall that this is the probability that we choose the action times what we see if we choose the action. This is an unbiased estimate of lit. And also what we'll use is that the square of lit tilde in expectation is how much? It is qit times lit divided by qit, all this together squared. So this will be lit squared divided by qit. And so what we'll see is that here lit is at most 1, so the expectation of lit tilde is at most 1, and also the expectation of the square is at most 1 over qit. And this gives us much better guarantees than what we would be getting if we were only using this bound here, which we were using so far. And indeed, this is now the first thing that we'll be doing. We will have to reanalyze the multiplicative weights algorithm. Now we'll reanalyze this in the sense that we allow these lit tilde to not only be between 0 and 1, but to be arbitrary, not quite arbitrary, but to be much bigger than 1. But then our regret bound will also depend on the squares of the lit tilde, but as we see, it is also possible for us to take the expectation of the squares, which then will turn out to be important afterwards when we turn this into an algorithm or when we reanalyze what we're getting for the bandit feedback. The first thing that we should do now when analyzing this EXP3 algorithm is to derive a refined bound for the multiplicative weights algorithm. So I've written down again what matters now. We are initially setting the weights to 1 and the pi's we're setting to 1 over n. And then in every step we perform this multiplicative weights update, namely wit plus 1 will be wit times this exponential change. And then we set the new pit to be equal to the wit, or the new pit plus 1 we set to the new wit plus 1 divided by their sum. So this capital W, this is just the sum of all weights. And as I was saying, we now just set this row here equal to 1. So we will, this will actually disappear now. We'll only have the eta floating around. This is the only parameter that we have. And for this, we will now show the following bound. If we fix L1 tilde through LT tilde arbitrarily, such that they are always between, all components are always between 0 and 1 over eta. Then the vectors P1 through PT when we set this row equal to 1, they fulfill the following. They fulfill that take the sum over all steps, the sum over all actions, PIT times LIT tilde minus eta times take the sum over all time steps, take the sum over all actions, PIT times LIT tilde squared. This is at most the minimum over all actions. Take the sum over all time steps, the LIT tilde, plus ln n over eta. This kind of a result, I hope, looks familiar, because this is exactly the kind of a guarantee that we also derived for the multiplicative weights method for the setting where these LIT tilde were between 0 and 1. Namely, what we are saying is, this is actually nothing but in step T, draw from the distribution P, because we have now, for action I, we have a probability of PIT. Now, this is the expected cost that you would get by this for your L tilde sequence. This is, at most, the cost of the best single action plus ln n over eta. And then we have this curious term here floating around, which is different from what we've seen before. Before, in our previous analysis of multiplicative weights, this didn't show up at all. We rather had here some 1 plus eta term. So this was like 1 plus eta times the cost of the best action plus ln n over eta. Now here this looks a little different, because now what we have is that here on this right hand side, or on this left hand side, we're subtracting actually eta times. And now what you actually again do is choose an action uniform or defined by the probability distribution pt, but now take the square of the respective cost. What this bound here implies is that this multiplicative weights algorithm is a no regret algorithm, because you can again bound this here by t, and so you can actually get the same kind of square root t times ln n bound, also derived from this, but only if you had experts' feedback. What we'll eventually do is we will use all of this as a subroutine inside our transformation to the bandit feedback. This is why I'm also not writing here that this is the action that we're choosing in step t, but I'm rather just writing the pt's, because eventually we will use the qt's as the probabilities that we choose certain actions. Good. Setting all of this aside, this is the kind of bound that we want to prove, and we prove it more or less the same way as we proved the bound for the multiplicative weights algorithm. And by that I mean the original bound for the multiplicative weights algorithm. Namely, how do we do this? What we'll do is we'll again use the sum of the weights as a point of comparison, and let's first talk about the sum of the weights that we see eventually after the last step. This is at least the weight of expert I, or action I, after step t, before step t plus 1. And how would we get this here? What is the cost, or what is the weight of action I after step t plus 1, after step t, before step t plus 1? Let's go back. This is just determined by this formula here. And what we'll see is that this is nothing but take the product of all these exponential terms. Which is nothing but e to the power of minus eta times the sum of these costs of action I. This holds for every I. And what does this tell us? This tells us that if we now take the ln of this final weight, this will be at least minus eta times the minimum of the sum of the costs for taking the minimum over all actions. So take the minimum over all actions, what's the cost of this action? And this is what we have as a lower bound for the final sum of the weights. Now we'll derive an upper bound also on this term, which then relates to the cost that our algorithm incurs, or more precisely, what we see here on the left-hand side. Because what we already have here is what we see here on the right-hand side. So what is the sum of the weights after step t before step t plus 1? This is nothing but the sum of the weights. And so we can again use just the formula for this. But now what we'll do is we'll use an upper bound on this term. Namely, what can we do? We can use that e to the power of z is at most 1 plus z squared for every z between -1 and +1. Why is this true? Well, that's actually no real surprise. When you plot these functions, then you'll see exactly immediately what's happening. This is the exponential function, and you can upper bound the exponential function by this quadratic function here. This is of course not true much beyond this point here, where we are at 1. So there we have a 3 here and 2.7, namely e here. And then of course the blue line will get much steeper than the red line, so there will be an intersection between the two, not far to the right, but between 0 and 1, this, or between -1 and +1, this looks like this. So if we plug this in up here, then we'll see, okay, this is at most the sum of the weights before step t times 1 plus, or 1 minus eta times lit tilde minus plus minus lit tilde squared. By the way, here we're using that these lit tilde are not too big, because otherwise this wouldn't be true. We wouldn't be allowed to use this bound. But because of this assumption, we can apply this bound and then get immediately here. Good. Now how can we rewrite this? How big is this? This will be the sum of the weights before step t minus eta times the sum of the weights before step t times lit tilde plus the sum of the weights times eta lit tilde and all of this squared. Now, what can we replace this such a weight by. How big was such a weight? Well, recall that PIT was nothing but small lit divided by capital small wit divided by capital W. So what we're getting here is nothing but the sum of the weights minus eta times the sum of all PIT times the sum of the weights times LIT tilde plus eta squared times the sum of all PIT times capital W T times LIT tilde squared. So this is nothing but capital WT times 1 minus eta times the sum of the PIT times LIT tilde plus eta squared times the sum of the PIT times LIT tilde squared. And from this, what were we bounding here? What were we rewriting? We were actually rewriting just the sum of the weights after step T. This is, we now follow this, at most this much. So we can say the final sum of the weights is actually no more than the initial sum of the weights times, and then we just take the product of all these terms. And let's now again take the logarithm on both sides of this equation. Don't forget that this is just n, the sum of the initial weights, so this will be at most ln n plus the ln of the following sum ln n plus the sum of all ln 1 minus eta times the sum with the LIT tilde here plus eta squared times the sum with the LIT tilde squared. Now, how big is such a term? We can now use another bound, namely that ln 1 plus z is at most z for all z. which tells us that we can also bound here this term by ln plus the sum of all, and now just take minus eta times the sum where we have the lit tilde plus eta squared times the sum where we have the lit tilde squared. Good. So nothing's really happening here except for that we use just some nice bounds regarding the exponential function and the logarithm. So we now have an upper bound on the on w, capital W t plus 1, on the sum of the weights that we reach eventually. And before, we've already determined this lower bound, which turned out to be this much. Now we can clearly just combine this and this bound and divide by 1 minus eta. So if we combine these two bounds, what will we get? We will get that minus eta times the minimum of the sum of the lit tilde is at most ln plus, and now we can just copy this from up here. I'll not do it quite literally. I'll now write minus eta times the sum over all time steps, the sum over all actions, pit times lit tilde, plus eta squared times the sum over all time steps, the sum over all actions, pit times lit tilde squared. And if we now divide this entire thing by minus eta, then what do we have? Let's once again write this. We will see that the sum over all time steps, sum over all actions, pit times lit tilde minus eta times the sum over all time steps, sum over all actions, pit times lit tilde squared. This will be no more, the sign flips of course because we're dividing by a negative number, this will be no more than the minimum over all actions, the sum over all time steps, lit tilde plus ln over eta. And this is exactly what we claimed. Fantastic. So let's once again see how this proof worked. It worked more or less the same way as our original analysis of the multiplicative weights procedure. The details are a little different, but the general perspective is just the same. We take the sum of the weights, the final sum of the weights, we use as a point of comparison. We use a lower bound on this to compare to the best action that we have, and we use an upper bound on this to compare it to our algorithm's performance. And this way, by having this sum of the weights in between, we can now bound our algorithm's performance in terms of the best single action. And what's happening here again is comparing an exponential function to a quadratic function and to a linear function, so to say. This is also something that we did in the original multiplicative weights analysis. There we actually compared the logarithm to a linear and a quadratic function. Now in this step here we're doing this comparison of the exponential function to a quadratic function, but the spirit is just the same. So there are certainly technical differences, but it's actually nothing technically new what we're seeing here. It is only a different analysis of the same kind of algorithm using slightly different bounds. But what is the advantage now? Now this statement does not require that these lit tilde are between 0 and 1, but there's only a weaker thing that we require, and maybe let's go back to the statement of our lemma, namely that these lit tilde have to be between 0 and 1 over eta. Cool. Just as a side remark, I said this before, but where do we even use that that the lit tilde are no larger than 1 over eta? It's exactly in this step here. Otherwise, we wouldn't be allowed to use this inequality here, because the z, which we set to be eta times lit tilde, this is between 0 and 1. It wouldn't be if we were not assuming that the lit tilde are upper bounded by 1 over eta. Good. Now, equipped with this refined analysis of these multiplicative weights, we will now turn to the analysis of our overall EXP3 algorithm. Now we can come to the analysis of the EXP3 algorithm. Once again, this is our algorithm. I've already removed the row here because we're setting the row to 1. And we have already a bound for this blue part here. We have already an understanding what this PIT times LIT tilde would look like. And this does have something to do with what we're doing in our actual algorithm. Of course, there we're not actually choosing actions with probability PIT, but it's rather this QIT. And we are not incurring costs LIT tilde, we're rather incurring costs LIT. Nonetheless, we can use the bound that we've obtained to now analyze this overall algorithm. And we do this exactly the same way that we analyzed our basic algorithm last time, for which then we used just this part here as a black box, which we didn't actually look into. And we only used the regret bound of this part. Now we have our refined bound, and then at a certain point we can get just some extra mileage out of the refined bound, which is just enough to get us a better bound. Namely, what do we want to show? We want to show the following theorem. If eta is at most gamma over n, EXP3 has expected cost at most take the cost of the best single action, LIT, not LIT tilde, just the actual cost, plus ln n over eta, plus eta times n times t, plus gamma times t. And how do we prove this? As I was saying, we prove it more or less the same way as we were doing also our analysis of this basic algorithm last time. How did we do this? Well, let's first fix I1 through I capital T arbitrarily. This, of course, fixes also these fake vectors that we're using for our multiplicative weights update. And this way also these p's that we will be seeing, those are also now fixed. So what is it that we're getting? Let's first see what our algorithm's cost would be on the fake sequence. So it is now the QIT times LIT tilde. What would that add up to? The QIT, we know what those are. Namely, QIT is exactly 1 minus gamma times PIT plus gamma over n. So let's take that apart. We'll get this 1 minus gamma times the first double sum with the PIT times LIT tilde plus, and then we'll have gamma over n times the second double sum. We will just have the LIT tilde. Now for this, we already have an upper bound, because this we exactly bounded via our lemma. So let's plug in the bound that we obtained from our lemma. This was take the best action. What's the fake cost of the best action? What's the best tilde cost of the best action? Plus ln n over eta. And then we had this curious term where there's the squares showing up. And now let's just copy this second part here. Good. Now let's move the 1 minus gamma inside here, or not quite. We'll see this 1 minus gamma, this is of course at most 1. So we can bound it by 1, and we can say here for this first term we're indeed just bounding it by 1, also for the second term. Now we are not bounding it by 1, because if we move it inside here, then what we're getting here is 1 minus gamma times PIT, which is at most QIT. Good. So, if our algorithm was actually incurring costs that are determined by these L tildes, then we would now have an upper bound on the cost that the algorithm incurs, namely this much. But this is not what is happening, because what is actually happening is that the algorithm incurs costs depending on the L's, not the L tildes. But what can we still do? Well, let's start slowly. How are these LIT tilde and the LIT related? I hope you recall. Namely, however we fix the actions in the first t-1 steps, the expectation of LIT tilde conditional on the first action being I1, the second action being I2, and so on, up to the last action before this being IT minus 1. This is exactly the probability that we choose action I in this step, conditional on whatever happened before. And this we then multiply by LIT divided by QIT, because this is the value of LIT tilde if we're choosing this action. If we're not choosing this action, then the value will be 0. And this here, this is nothing but QIT. So what this is nothing but LIT. And so the expectation of QIT times LIT tilde is nothing but the expectation, the sum of the expectations of QIT times LIT tilde. And now we can again do the magic that we did before, namely move out the LIT. Why that? Because we saw for every fixed choice of I1 through IT minus 1, this is always at least exactly equal to LIT. And this QIT, this is now still a random variable, but its expectation is exactly the probability that we choose action I in step T, and namely it is the a priori probability. So what this is nothing but the expectation of LIT, of the cost of our algorithm in step T based on the action that we're choosing in step T. Good. How does this help us? This helps us quite a bit because we can now see that what we have here in expectation. If we are now taking an expectation, what we have here on the left-hand side, this is exactly the expected cost of our algorithm. Now what else do we have? We have this part here, and we have this weird part here, and this part. And in all of them, there's still the lit tilde showing up. Here it is even showing up with a square. So let's talk about what we get if for this term here, where we have the square. Well, we have the square, so condition on any choices we did before. What is the expectation of lit squared? It is exactly qit times lit. This is of course the expectation of lit tilde squared, and this is exactly equal to lit divided by qit squared. This we get, this is the value that lit tilde takes if we choose action I. This happens with probability qit, otherwise it is 0, so this will be exactly equal to lit squared divided by qit. This holds again for all I1 through it minus 1. So what is it that we're getting? What's the expectation of qit times lit tilde squared? Well, if we first talk about this in the conditional probability space, maybe that's even easier. Then it is nothing but take the sum over all actions, qit times lit squared divided by qit. So this is nothing but the sum of all lit squared. This again holds in every conditional probability space, regardless of how we got here, and therefore we can also consider this in the unconditional probability space. Good. Now we can plug all these things together. If we now take the expectation of both sides of this inequality, then we get something good. Namely, if we take the expectation of the left-hand side, What was the left-hand side? This was the double sum of all qit times lit tilde. And this we can bound by the expectation of the minimum of all I, take the sum over all time steps. What's the lit tilde that we're seeing? Plus, how does it go further? Now we'll have here the ln n over eta. Plus, then we get a double sum and then we have the curious expectation of qit times lit tilde squared. And then we have this last term, which is this here. So it is gamma over n times the double sum times the expectation of lit tilde. This thing here, we exactly know how big it is, namely it is nothing but sum of the lit squared. This here, this is the expectation of lit tilde, this is nothing but lit. And what do we know about this? This here is at most the minimum of all I, the expectation of the lit, the sum of the lit tilde, and this is nothing but the minimum over all I, the sum of the lit. And what do we have here on the left hand side? This is nothing but the expected cost of our algorithm. Where was this coming from? So for this bound here, this is just coming from here. This bound is coming from here. And here we're again using this bound. And where is this coming from? This is what we have here. Now, how can we bound our sums here? How big is one of these lit squared? This is no more than 1, so this here will be at most n. This will also be at most 1, or altogether this will be no more than n times t. Also this together will be no more than n times t. And along the way we lost one of our etas apparently, because there was an eta floating around here which we unfortunately lost. Let's just plug this in back in here. So how big is this in total? This is now the expected cost of our algorithm is no more than cost of the best single action plus ln n over eta plus eta times n times t plus gamma over n times t. And this here is nothing but gamma times t. And I hope this is exactly the bound that we claimed before. It is. So also this analysis works no different from what we did last time. The only difference that now occurs is that we also have the expectation of Lit tilde squared inside our bound. But to understand this, we just do the same things we were doing before, and then eventually we can fortunately bound these things in a way that we also get to the desired bound. So far, this actually doesn't look any different from what we did last time. Well, it does maybe look... No, it's not even clear whether this is any better than what we derived last time. There, our bound looked very similar, but the advantage is now that we can again choose values of eta and gamma. And what will actually be important is that here we never have this eta times gamma, but we only have here eta times n times t, or we have here gamma times t, and we have ln n over eta. And how would you want to choose the etas and the gamma so that this is good? Well, what you can do is you can do the following. We can set eta to be square root of ln n over n times t. We can set gamma to be n times eta. Then, what will be our external regret? Our external regret will be at most, and it is now what we see here. Plug in eta, so then we'll have, for all of them, n times t, the square root of n times t times ln n. Because this here will be exactly n times square root of n times t times ln n. This here will also be exactly equal to square root of n times t times ln n. And also this here will also be exactly equal to square root of n times t times ln n. Cool. So this buys us a lot because now our dependence on t, and don't forget t you should think of as being much bigger than n because we're playing this for a long time. So this is why we're primarily interested in how the bound depends on t. This is now a square root rather than t to the 2/3. So of course both were no regret algorithms, but now our bound is indeed better. It is again a square root t bound. Like we also obtained this for the full feedback case. There the bound was a little bit better. We had 2 times square root t times ln n without this n here. So that was only logarithmic in n. Now we also have a square root of n here. But indeed this is necessary. And this is what we will show next time. We will show that, well, no, we won't show that this has to be worse here than it has to be for the full feedback case. This is not what we will be talking about, but we'll talk about this dependence on the t. At the same time, I want to tell you that actually this is the optimal bound that you can obtain for this setting, like also the bound that we have for the full feedback case where we don't have this n here. This is also the best possible bound. I'm not so sure about the constant factors, but let's not talk about the constant factors. But what we'll show next time is that at least it has to be this big, even if there are only 2 actions. Good. But what is still important, and let me once again tell you this as the bottom line of all these no regret algorithms that we've seen so far, is that even with very little information, with very little feedback, you can choose actions in a pretty good way. So even if you don't know what the cost of the other actions are that you did not choose, by just adding some exploration, you can figure that out. And although you're playing against an adversary, at the same time, the benchmark here is of course much weaker because you're comparing to the best single action, you're not comparing to the best action sequence. With this, I'd like to conclude for today. As usual, please do let me know if you have any questions. Stay safe. See you next time. Bye.